Okay, so welcome to Friday. So I'd like to introduce Jun-Muk Hwang from Daejeon in South Korea, where they have really good chalk. He's brought his own. He's so well organized. Okay, so characteristic cone connections.
Thank you. Thank you for the invitation to this very interesting program, Twistor theory, and also the chance to speak here. It's sort of an advertisement of this characteristic conic connection, which I think is an important object. I think Twistor people had been using it for a long time, but just they didn't put a name. So the name is not very funny because with the naming more, we call it characteristic conic connection. Maybe Twistor people would have called it more interesting name. Okay, so this is what I present today is a joint work with Chi family. And all objects in this tower are holomorphic over complex numbers. Some of them naturally hold most of them naturally hold in dual analytic category, even simple, but I prefer holomorphic category. So let me start with fixing some notation. V is a vector space of dimension n. And then we have this projectivization, and I consider a submanifold of the projective space. This is let's just consider compact submanifold, compact complex submanifold. So this is equal to, in algebraic geometry, this is smooth projective variety. And then I will use this notation, z hat inside the vector space. This is the affine cone. So z is just projectivization of z hat. And then I will use this notation, aught z hat. This just means linear transformations that preserve z hat.
Could you define an affine cone?
Affine cone means any object in projective space is lines in the vector space. A projective space is union of lines in vector space through the origin. Z hat is just collection of all lines through corresponding to Z. So this is a naturally linear subgroup. I will denote by small aught Z the Lie algebra of this group. So that's the notation I will use throughout this talk. Now let's start with definition. So we consider n-dimensional manifold, complex manifold. And then we consider the projectivized tangent bundle. This is just a union of the projectivization of its tangent spaces. Then we consider a submanifold. Is a Z cone structure on M. So this is what I like to define. If each fiber fiber of this projection. There's a natural projection from C to M. It's a submanifold inside here, so there's a projection. So each fiber, so at each point, so which I denote by C script C lower x, and so this is just fiber at x. So this is inside PXM. So if this each fiber is projectively equivalent to the fixed submanifold in projective space. So this is projective equivalence. Isomorphic, linear isomorphism. Then we call it a Z-cone structure. All right, so let's, before giving examples, let's recall this this concept of frame bundle. So let's see. Frame bundle. Frame bundle is what? So each frame bundle of the manifold is a union of frames at each point, and this frame at a given point just means set of linear isomorphism from V to the tangent space. And then, so this is a GLV principal fiber bundle. Now, given a linear subgroup, a G structure on M, G structure on M means a G principal subbundle. That's a classical terminology. Whenever you are given a group, a subgroup of linear group, a G structure on M just means you have a choice of principal subbundle with that structure. And it's more or less tautological that this definition of G-cone structure. So there's a natural one-to-one correspondence between Z-cone structures on M and auto Z-hat structures on M. So in other words, this means G structures with G equal to the auto Z. There's natural one-to-one correspondence. This is easy to see. Just consider, maybe I'll skip this. So G-cone structure is something very classical. It's just a special case of G structure. But the difference, I mean, the main point is that you somehow change the viewpoint. Instead of group, you look at a projective variety. That's the change of viewpoint is the main. So let's look at some example. When Z is something familiar, some examples which are familiar. When the projective variety is just a linear subvariety, then Z's cone structure on M, this is just distribution. Rank. Just a subbundle of tangent bundle. something very familiar. And then example 2. When Z is quadratic hypersurface, is a quadratic hypersurface. Then Z cone structure on M. This is nothing but conformal structure. So this is something we heard a lot in this week. So something many people start. So another case which I know have been studied by Twistor people is the case where Z is. This is a notation algebraic geometry used. This is the rational normal curve. Of degree n-1. In this case, Z cone structure. There are people use different names, but I think Matthias used this terminology, para-conformal structure. But some people call it GL2 structure because the group is GL2. But different representation of GL2, depending on the. So this is an n-dimensional representation of GL2. So these are objects that have been studied in Twistor theory, but in algebraic geometry there are much more diversity of choices of such structures, because you just pick any projective submanifold, then you can consider such structure. Now we call this also classical things.
I mean, often there won't be any automorphisms.
Often there's no automorphism. Only, by definition, there's just a scalar multiplication.
So you just lose Z in the
Yes,
structure.
but even in that case, because of the geometry of Z, there are lots of interesting theory of this construct, even when the group is trivial. Okay, let's look at this. For G structure, so it's a principal subbundle of the frame bundle, a principal connection, which also appeared many times this week. A on P is just a G invariant subbundle A in the tangent bundle of the principal bundle such that the tangent bundle of the principal bundle splits. That is the definition of principal connection. Now there's some corresponding. So here, up there, we have a correspondence between. Seems to be nice pointer here. So you have this one-to-one correspondence. Now you wants to look at the. In this side, you have this nice notion of principal connection. What is the corresponding object here? Object corresponding to principal connection. So that is something I like to define. So this is the next definition. So we have a cone structure, Z cone structure. such object has what's called the tautological distribution. So let's define this. Whenever you have a cone structure, there's a natural tautological distribution. And I will use this notation, J. So this is a distribution on the cone structure, tangent point. And this is defined by so C is inside projectivation of M, and then you have a projection to M, P, and let's choose a point here, alpha, which goes to point X. Then you have, of course, the derivative of this map. Your derivative of this map. And then inside here, you have the affine cone of that point, the one-dimensional subspace corresponding to alpha. So, and then we define J alpha to be D alpha T inverse, which naturally contains kernel. So this is called the characteristic, tautological distribution. Whenever you have a cone structure, there's natural distribution coming from tautologically. Now, then we define a conic connection. So this is something we want to define. A conic connection on the cone structure is a line subbundle of this tautological distribution such that J is split. That's the definition of connection. Connection on cone structure is conic connection. The name conic connection I find in the book by Manin on the complex geometry and gauge field. Maybe it's invented by Twistor people. So that's the name, conic connection. And then, so what is a conic connection? It's conceptually, conic connection is roughly, this is path geometry in C direction. It's a path geometry on the manifold, but we only consider in the direction of specified by the cone. So especially projective connection is a special case of conic connection. The usual projective connection is a special case of a conic connection when Z is the total space. Okay. Now, usually conic connection arises in the following way. So, if P is a auto Z hat principal bundle, a structure associated a Z cone structure, then for a principal connection, A on this principal bundle, we have associated affine connection on M. And the associated affine connection defines associated geodesics. geodesics. So the associated affine connection determines a conic connection by the leaves of its geodesics. Conic by geodesics, by delta A geodesics. In other words, when you have an affine connection, it determines a principal connection, a projective connection. And this projective, so path geometry. This path geometry preserves this cone structure because this principal bond is auto-jihad. And this induced conic connection from the geodesic of the conic connection of the connection, the principal connection. So it's called, we call it the geodesic conic connection. Okay. That's something I define. Okay. That's a name. So one way to get conic connection is just to you choose a principal connection, then the geodesics of the connection give you a conic connection. That's one way. Any questions? Okay. Now there's a sort of converse to this. So this is the proposition. This is relatively easy, but I don't know whether anybody before us proved this. But maybe some people know. But this, I think, have not been published. So this is not very difficult, but useful. So assume the following property. This projective submanifold, this smooth projective satisfies. Perhaps the reason that this was not really formulated in differential geometry is the conditions are typically algebraic geometry. It's very, very common notion in algebraic geometry. So the holomorphic sections of the O1 bundle on the projective space on the submanifold is just V star. In algebraic geometry, this is called linearly normal. So G is linearly normal. Second condition is that the tensor product is surjective. And this condition is a special case of what's called projectively normal in algebraic geometry. But anyway, let's assume these two conditions for the projective variety. Many natural, almost all naturally arising projective variety satisfy this property. Then any conic connection on a G cone structure is the geodesic conic connection of a principal. associated. O2G structure. It's something easy to show. In other words, what we just say here that a principal connection, the usual principal connection on principal bundle induces a geodesic conic connection. This is typical. In most cases, any conic connection arises from that construction. So this shows that conic connection is not very new object. It's essentially coming from principal connection.
Does this condition say anything about the group G? Probably not.
Not much. But condition like this is non-trivial, even when the group is trivial. Even when there's no automorphism group, this kind of condition is non-trivial. So what we have so far in this correspondence is that you have Z-cone structure, and that's one-to-one correspondence with O2G hat structure. You have this one-to-one correspondence, and then now you have a conic connection on here, and here you have a principal connection. And we saw over there that any principal connection gives conic connection geodesic. And this proposition says that any conic connection comes from principal connection when you have 1 plus 2 condition, which hold in most cases. So you have this nice correspondence. All right. Now the next thing is the most important definition. So far it's very formal. And also in geometry, principal connection, and there are lots of them, sometimes not very useful. But we want some special property of this principal connection. That's when it's useful. And here the key definition. This is the key, which is in the title of my talk. Is the following: a conic connection is a characteristic connection and this is the important book. If we satisfy this condition. So here, dj means that this is the distribution spanned by this, the Lie bracket of J itself and J. So it's just a derived system, what's called derived system of. So characteristic conic connection means that it has this property. Why is this important? So this is says that this system, this distribution, descends to the leaf space, the space of leaves of connection. In other words, in terms of geodesics, this condition means that you have some interesting distribution on the space of geodesics. And this is exactly the Twistor correspondence. It's hidden here. So in that sense, it's important. So Because when you want to study the geometry from the point of view of space of geodesics instead of the space, original space, as Penrose said, the space of light rays, that correspondence works when it satisfies this property. You obtain some interesting system on the space of light. So that's why this property is important. Right. Now, what is the example? Let's look at some example of characteristic. Then you can see why it's important. So, first example, as before, these linear subspace. So that this cone structure is a distribution of rank chain. Then this admits, so this admits a characteristic conic connection. Let's just say characteristic connection. You can check this. It admits characteristic connection if and only if the distribution is integral. So the resistance of a characteristic connection is equal to integrability of the distribution. Now, there's something interesting one can say. Because of some standard algebraic projective geometry, except example 1, a Z cone structure. So if a G cone structure has a characteristic connection, then it is unique. So the case where Z is a linear subspace, this is the only case where it can have many characteristic connections. Unless it's a linear subspace, if it's non-linear project domain, then any G cone structure, if it has a characteristic connection, then it is unique. So there's something canonical about characteristic connection.
The condition 1 is not satisfied in this case.
In this case?
In example 1.
In example 1. Yes, it's not satisfied. So I didn't say that in this case, this proposition is not guaranteed. But this, what I'm saying here is nothing to do with proposition 1. Just except in this case, in any other cone structure, whether it satisfies this property or not doesn't matter. Any other cone structure, except the linear case, has a unique characteristic connection, if it has. Usually it does not have. And example 2, when Z is the project, then this is conformal structure. And then, in this case, the typical null geodesics of the Levitz-Vita connection over Levitz-Vita. Actually, any choice of Levitz-Vita gives null geodesics. And the null geodesics give characteristic connection. On the associated structure. So this is something people study much. And this is also is a typical, I mean, you can sort of understand characteristic connection as a natural generalization of null geodesics, Levitz-Vita null geodesics on general construction. And example 3 was our rational normal curve. Now, this we call the paraconformal structure. And many examples of paraconformal structure comes from ODE. So if a paraconformal structure comes from this is what Mathiez actually studied. Certain ODEs satisfying some vanishing of some invariance define paraconformal structure. So many paraconformal structure comes from ODE. And if it comes from an ODE, then there's a characteristic connection. So in many settings, many natural geometric settings, you have natural characteristics. Now I'm in trouble. Questions? And example 4. Example 4 is, if you recall, maybe you have forgotten what, maybe you haven't attended, but if you recall 9 MOOCs talk on Wednesday, there was what's called VMRT structure. And I'm not gonna define it here, but so this means that many cone structure arising from what's called minimal rational curves. In algebraic geometry, I have characteristic connection. So the point of these examples are that this definition, which may look somewhat very special, but it's actually something very natural. And there are lots of examples with conic connection, characteristic connection on such cone structure. Now let's make one definition. So let's choose a point in the affine cone, different from the vertex. And then we denote by TU Z hat the tangent space of the affine cone at the point. But this is now a linear subspace in V. And this is what in algebraic geometry is usually called affine tangent space. At that point. we regard it as a linear subspace of the vector space. Then I introduce the following chi z. This is homomorphism from very square V to V, such that when you take pairing of a point with affine tangent space, this lies inside the same vector space for all u. So this is a definition. It's a definition of special subspace inside this homomorphism space. Determine it's a subspace associated with given any submanifold, you have any projective submanifold, you have this natural class of homomorphisms. Okay. So what I'm trying to say is this, so we have this notion of characteristic conic connection. And many conic connections come from principal connection. So what is the relation between between characteristic connection and what are the corresponding principal connection? And this is our main theory, the first main theory. Say that if Z is C, is so this is Z cone structure, and P is associated auto Z principal vector. And let's say that you have a principal connection A. And given a principal connection, you have the natural associated torsion, this torsion of A. And this is just a function with values in this space. Function on P, on the principal bundle. It's a function on the principal bundle with this value. This is the classical theory of principal bundle. Then, geodesic conic connection. Of A is a characteristic connection. If and only this torsion has values. The torsion is a function with value in this vector space. If the torsion of the connection has values in this smaller vector space, then the geodesic connection is a characteristic connection, and vice versa. And any characteristic connection, okay, yes, and vice versa. So this, in this correspondence, so let me see. So you have this correspondence between cone structure and principal bundle, G structure, and conic connection and principal connection. And here we have a special kind of conic connection, which we called characteristic connection. And this exactly corresponds to a principal connection with torsion inside here. That's the relation. And there's an immediate corollary. So one corollary of this theorem is that the geodesic conic connection of a torsion-free connection is a characteristic. Of this cone structure.
Could you raise that? Because it's
The geodesic conic connection of torsion-free connection is a characteristic connection because torsion-free means that torsion has values in 0, and 0 is certainly inside this space. And this generalized example 2. Generalize. Then the null geodesics of Levitt-Beta connection gives characteristic connection, and that's exactly Levitt-Beta connection is torsion-free. So the associated conic connection is characteristic connection. So that's generalized. But this is you will see that. There are many characteristic connections which do not come from torsion-free connection. Because this space is much bigger than 0.
So is the situation that you have an equivalent, some equivalence class of different connections? For example, in example 2, on the quadrant, there's no connection that comes from a global. I mean, you have local.
And this is so-called completely local geometry. Now let's recall this notion of Spencer homomorphism. Of linear algebra. That is just operator from which send an element here to an element there, defined by just HU. Classical. And this theorem has the following corollary, combining with the classical theory of connections. So assume Z satisfies. It's a projective manifold. Now assume that it satisfies 1, 2 in the proposition with linear normality and kind of projective normality. And then, and additionally, 3. 3 is this chi z is inside image of the Spencer operator. Of course, the Spencer operator depends on choice of the algebra. So this is for all the algebra, the automorphism of the product variety. So let's assume that the variety satisfies these three properties. One, two, and this property. Then for any Z constructor admitting a characteristic conic connection, the associated auto-Z structure principal bundle as torsion-free. This is because if a principal connection has a torsion inside image of the Spencer operator, then you can choose a new connection which is torsion-free. Now, if it's a characteristic connection by this theorem, the torsion must lie inside this space. But by the assumption of the geometry of this projective variety, this space is inside the image of Spencer homomorphism. So there must be a torsion-free connection. So many examples of like those examples coming from algebraic geometry. As long as it satisfies this condition, that this space is inside the image of homomorphism, Spencer homomorphism, then it's always torsion-free, and that gives a lot of restriction on geometry. So what are the examples satisfying 1, 2, and 3? It's not easy to find the example satisfying 1, 2, and 3. As I mentioned, these 1 and 2 conditions are very common in algebraic geometry. Any naturally arising projective variety usually satisfy 1 and 2 conditions. But this condition 3 is very restricted. So the reason that this result is strong is because of this condition. And this condition holds only for very small class of projective variety. But here's our theorem. So we checked it for the parameters. Now S is simply algebra. Not of type S exclude simply Lincoln diagram type of AL, where L is bigger than or equal to 3. And Z is what's called adjoint variety of the Lie algebra. And this just means that it's a unique closed orbit of the adjoint representation on the Lie algebra. Then, by the way, this is the Wolf space of the Cottonian Kellerman. The twistor space of the Cottonian, symmetry Cottonian Kellerman. So this is, then Z satisfies 1, 2, 1 and 2 are classical. That is the highest rank orbits of irreducible representation satisfy 1 and 2, the classical. But this 3 is what we checked, and that's the hardest part of the calculation. And for types, this type, 3 is not all. And this exclusion is necessary. Okay. And what is the purpose of this? So there's some, I will now tell you some application in algebraic geometry. But so far it's completely differential geometric theory.
So when you say there exists a torsion-free connection, it's not unique and it's only locally defined. So near every point?
This, locally, everything is local, but and sometimes depending on the group, in most cases, torsion-free connection is unique. If the Spencer operator is injective, and in most irreducible representative, except some cases, this Hermitian symmetric space, the Spencer homomorphism is injective, which means the torsion-free connection is unique. Like conformal structure is one of the exceptions. So in this case, for example, for this group, for this type, except the type C, the torsion-free connection is unique.
What's the homology of this connection? What's the homology of this connection?
Okay, this is a G structure. So holomorph is contained in the group G. Okay, so let's see. I'll explain briefly the application. What is the purpose I did it? This may have other implications, but the main motivation for me was studying, as Jun-Muk said on Wednesday, a minimal rational curve. This, if you have algebraic geometry, just consider it's a kind of minimal guys among rational curves on a projective manifold. And when you choose a general point, then the deformations.
So when I say minimal degree, it's clear, right? There are too many uses of the word minimal in algebraic geometry. Minimal degree.
Minimal degree, say, with respect to some polarization. But, well, maybe you embed such that these are lines, that's fine. So deformations of C fixing X determines some projective subvariety. And often they are smooth because of minimality. So you have this. And often, or sometimes, the type of this projective variety. This is what Jun-Muk introduced as VMRT-LX. The type of this projective variety determines the neighborhood complex analytic neighborhood of this curve is determined by the type of this projective variety. Quite often this, not always, but there are many cases where this happens. And what Jun-Muk explained is that if you assume like X is final Picard number one, then the neighborhood determines the manifold. So this has application in algebraic geometry. And on Wednesday, he mentioned a few cases where this holds. But the new case we have here is this. So what we can prove was that if the CX is equivalent to in corollary, in theorem 2, equivalent to this adjoint variety, then neighborhood of C is either, there are two cases, either neighborhood of a line, of a minimal rational curve, in a very special type of construction, blow-up construction from projective space, or a neighborhood of enumeration curve. It was called the wonderful group compactification. Of group of the Lie algebra. There's a construction in algebraic geometry, the compactification of the group corresponding to the simple Lie algebra called the wonderful group compactification. And for this, the minimal rational curves are determined. There is kind of unique such class. And for this class of curves, the VMRT is exactly this. But these two cases has different neighborhood. The geometry is different.
Is that the adjoint group of A? Which group? I mean, you have Lie algebra.
Group of S. The group of the Lie algebra. Simply.
Which one? Is simply connected or the adjoint?
Adjoint group. Okay. So this is one application. And it comes from applying this theorem 2 and construct a torsion-free connection. And then let me just mention that then we use this classification of torsion-free holonomy here, this Marukov-Shubakov form. Classification of torsion-free holonomy, and this gives that for this class, if you have a torsion-free connection, then it must be locally symmetric. So these two are the possible locally symmetric structures.
Okay, thank you very much. Any more questions, please? Yeah, Matt, check.
So you mentioned there is application to ODEs.
Yes.
And the question is that in the case of ODEs, if you have a fourth order or third order ODE with this GL2 structure, then this connection you're referring to is torsion-free.
Yes.
But for ODEs of order 5 and higher, except the symmetric space in order 5, there is always a torsion. But this torsion takes place in a kind of smaller representation space. So Merkulov calls them little torsions.
Okay.
Are these connections you're constructing always in the smaller representation space than the whole space?
Yes. It's, as I say, this ODE case gives connections, characteristic connections. So the torsion must lie in this small set I mentioned, this chi z. The torsion must lie inside here. I don't know whether what they call small torsion is here, but actually I think for OD it's even smaller. There's an even smaller space. But from our theory, it must lie inside here because it's a characteristic connection.
Maciek is looking unhappy.
I'm looking happy.
Not happy. Okay. Hard to tell. Okay. Any other questions, please? If not, let's thank Jun-Muk again.